Yeah, thanks a lot. Thank you for the introduction, and thanks everyone for coming. And also thank you for inviting us here. It's been quite a nice series so far. So I'm very glad to be able to tell you more about the work that we've done, because obviously it's a team effort. Most of us are from Google Research, but we also have folks from University of Toronto and MIT. But so the work that I'm going to be talking about is about sort of a new functional programming language, specifically geared for scientific computing, that we call DEX, and that we've been working on for some time now. So just to give you a bit of a background before we actually get into the core ideas behind the language, I want to tell you basically where we're coming from. So as you know, I have worked on PyTorch, and then like the person who actually started the whole project, Dougal McLaurin, he sort of, I don't know, quite famously, I guess, wrote the Autograd package, which kind of introduced automatic differentiation to sort of the land of first order array libraries in Python, and sort of kickstarted this this whole process. And so we have quite a bit of experience with actually writing those libraries for Python, not so much necessarily sort of in programming languages background. But so what we now want to do, what we want to do is we kind of want to replicate the success of those libraries. And I think that the success of this approach, of this first order sort of embedding in Python, is kind of due to two factors. One is actually sort of easy hardware retargetability. Programs written in this style can be easily sort of executed on CPUs, on GPUs, on TPUs, or any sort of wide data parallel vector machine, and also automatic differentiation. And what's important is that those two features actually are not like completely separate features. They do actually interact pretty significantly. More importantly, those programs, like those languages, those embedded DSLs, they're usually just like, if you were to extract the programs that people sort of run from the host language, which is something like Python, they kind of look like sort of long lists of instructions where every instruction is kind of a big, sort of very heavily data parallel operation in itself. And people are kind of taught to program with arrays that are sufficiently big to saturate the accelerators on their own. And so what this means is that you can just apply sort of the standard sequential autodiff to a program like that, and you also derive a program which again is composed out of sort of parallel operations. Those languages, very importantly, are often closed under automatic differentiation. And so what's nice is that like you don't lose any parallelism as you perform automatic differentiation, even though you can do it kind of using the, let's say, I don't want to say naive, but sort of the basic automatic differentiation techniques that have been developed even for very sequential languages, right? But the result is still very parallel. So we basically want to take this, but obviously like first order array libraries have limitations. Not everything fits into them, and once something doesn't fit, you generally fall off a performance cliff. And there's also a pretty big expressiveness cliff once you're interested in things like branchy computations, ray tracers, physical simulations. So we kind of want to push on that front, but still kind of retaining the good properties that those languages used to have as we were working on it. So this presentation will kind of have two parts. First, I'll talk about sort of the surface language and the ideas there, sort of what the users of the language will see. And then the second part, if we have enough time, we'll see sort of how deeply we'll be able to go into that. But the second part will be more about the actual implementation and what do we have to do to, for example, make automatic differentiation work on a language that looks like this. So let's start with what users see. And as you might have seen in the abstract, sort of the core idea underlying all of DEX is sort of this unification of sort of array programming with just regular functional programming, right? Functions and arrays turn out to be very similar. And in fact, if you've heard or thought about representable functors, you might have already seen some of those ideas. Many of the things that I'll tell you today probably will not be necessarily novel and coming from us, but sort of I haven't seen anyone put them together in that way exactly. So just looking at the types, the way we write the function type index, it's just using the standard arrow notation, like in Haskell. So this is a function from type A to type B. Arrays are very similar. We also use an arrow, just a slightly different arrow, this like fatter arrow, and it also binds more tightly than the function arrow. So we kind of often just put those types much closer. Both functions and array both have both the function type and array type have an introduction rule. For the function type, it's a lambda expression, and for an array, we also have sort of a generator expression where roughly the idea, it looks almost exactly like a lambda, right? Instead of a lambda, you write for, then you have a binder of some type, and then you have an expression. And the idea is that the array is defined by evaluating this expression at sort of all of the values for x, for all the inhabitants of this type tie we will instantiate this expression and sort of memoize the result of this in an array. Similarly, they have extremely similar elimination rules. Both have basically application. In array application, usually we call indexing. And they also have very similar reduction rules, right? For functions, this is just standard beta reduction. For arrays, similarly, if you have sort of a pure array generator and you immediately index it, then you might as well avoid creating the intermediate array, and you could just like compute exactly the expression for the index that you're looking at. So basically, the similarities are very striking there. There are some differences, though, in basically how their performance looks like, right? For functions, construction is cheap. Usually, I don't know, if your sort of runtime supports first-class functions as values, like it's perhaps just a single heap allocation. For arrays, it's actually expensive because you do have to evaluate sort of this expression, or the expectation is that you will evaluate this expression sort of eagerly at the full domain of this type. Dually, the application is expensive for functions because, well, you actually have to run the body, but for arrays, it's fairly cheap because we've already pre-computed it. You just really look it up in memory, and the result is just waiting for you there. And the slight sort of symmetry or the duality breaks if you look at the domains, because for functions, the domains can really be anything, given that they're kind of lazy in how we evaluate them. For arrays, if you have an infinite domain, the generator expression will never terminate in an eager language. So index is an eager language, so in particular, we kind of restrict the domain of arrays to be finite. So just to give you a few quick examples of array types, the most basic one, let's say the type of 3D vectors of floats, this is how we would write this. You can already notice that we actually do not use just straightforward integers to denote sort of the domains. The fin here stands for finite, so this is kind of a type constructor, let's call it, that takes sort of the size, the number of inhabitants it's supposed to have. You can think of fin n as like the n-size prefix of natural numbers. It also accepts negative numbers, and then it's like an empty uninhabited type, essentially. But actually, dex also is our type system is actually also value dependent, which I'll also expand on a little bit later. And so what this means is that if there's some integer n in scope, it is also valid to be talking about arrays that have a type like this. Not every single expression will be possible to be treated as a type, but in particular, lifting variables into types is always possible in a type system that looks like that. Even though we kind of talk about 1D arrays as the fundamental array type, obviously you can compose them. This should read as it's n. So this is an n by m matrix, but really, if you were to look at how this is defined inductively, it's effectively a bundle of n m-sized rows. But of course, eventually in the backend, we will actually flatten this into sort of a single buffer. Again, for any n and m in scope defined in any way you like. And similarly, you can actually have functions that are polymorphic over indices, like the sum function. You might write it that for any type, this sort of question mark here indicates that it's an implicit argument. So sum will really take one explicit argument, which is an array of indexed by some indices n, and just returning the result. What might be surprising is that so far we're using this fin type for the index. You might try, for example, using integers as indices, and actually dex will complain that this is impossible. Dex will complain this particular error is because it can find a type class which is required to be satisfied by any type you put into an array index. Again, I will expand on this more a little later. So I am really happy, actually, that our talk is right after the presentation last week, because a lot of the motivation for what I want to say you now has been already kind of laid out. We kind of want to embrace sort of the people sometimes like point-free programming, but people often like very pointful programming, and that's also what they often do in mathematical notation, right? So just to sort of recap and show you how something like a matrix multiply looks in different languages and eventually in DEX. So in second-order array combinator languages, this is usually how this would look like, right? This is kind of a fairly point-free expression. There are some sort of binders for arrays, but generally like direct indexing into arrays is discouraged. You're supposed to kind of deconstruct array types using those combinators that satisfy certain algebraic properties. Then I just decided to actually include the einsum notation from a library like NumPy, because it also, I mean, it's a very restricted language because it's only for tensor contractions, but actually it is very concise. Something like a matrix multiply is kind of given by an expression that looks like this. So what this means is that the things before the arrow are arguments. So there are two arguments separated by the comma. the sort of iterators for the first argument. So it will be a 2D thing, and we bind sort of the first dimension to iterator I, the second one to k, similarly for the second argument. And then this gives the output and the iterators that will appear in the output. And any iterators that are bound to any inputs but don't appear in the outputs are sort of reduced over, right? The idea is that those are tensor contractions over some semi-ring. This in particular states that it's a matrix multiply, but you can do batch matrix multiplies or something completely different if you want. Similarly, this is the expression in single assignment C, which also actually looks very similar, in my opinion, to something like NumPy, although it is slightly different. And in fact, if you just look at the basic DEX expressions, they also look very similar to sort of the tensor comprehensions formalism that was discussed in the last seminar. So this is kind of the most basic form of the expressions we could give for a matrix multiply. So again, we have two loops, perfectly parallel loops, right? One over an n-sized index set and another over n-sized, and then sort of a dot product with explicit indexing. What's important, just like here, you have explicit indexing on arrays right there. We can simplify this basically by sort of its syntax trigger, just like you have, lambda, instead of saying lambda x, lambda y in a language like Haskell, usually it's just say lambda x, y, and then put the body. So we can just drop this second for. Then what's important is, again, this inference of bounds. Again, kind of similar like what single assignment C did, but as you'll see later, it is actually slightly different. But in this particular expression, DEX will be able to actually infer the bounds of the loops, and so we can actually drop them, which significantly shortens an expression like that. And finally, we can also drop the parents. It's kind of similar to block arguments extension of Haskell or something like that, I think, to basically arrive at this very, very simple expression. Again, kind of similar like single assignment C, but I don't know. To me, this reads pretty good as a sort of statement of a totally abstract statement of a matrix multiply.
Just to check, the Q's and K's have got mixed up somehow in the DEX.
Oh yeah, okay, yes, that's true. This should always be. Oh yeah, okay. I renamed the binder here, but I forgot to rename the expression. So yes, from that point on, you should substitute in the expressions Q's for K's. Yes, this is an error on the slide. I'm sorry for that. So here, just replace K by Q's. All right, but sort of to calm down the people who do enjoy point-free programming very much, right? The point here is that we actually want to give people the ability to program in a pointful way, but we're not really taking out any ability to program in a point-free way, right? Something like the combinator-based matrix multiply, it's still a valid DEX program, in fact, if you only define like a few combinators, which often end up to basically be one-liners in this pointful notation, right? It's similar like in Haskell. People do a lot of point-free programming in Haskell, but like the foundation of a language such as Haskell often is something, I don't know, derived like from system F, and that is actually pretty pointy. So having a foundation like that actually does not prevent you from doing point-free programming. It only increases your expressiveness to actually allow pointful programming instead of forcing people to sort of construct their expressions from like an algebra of point-free combinators. Also, another important thing is rank polymorphism. Rank polymorphism actually is not supported in DEX. In particular, if you see a type with 2 arrows, it is necessary sort of a 2D array. There's no opportunity to increase this. I might be completely ignorant in this, and I would actually be very interested in hearing counterexamples. But in my experience so far, the rank polymorphism, I've seen people use it to achieve batching of the code. Like they have basically multiple sort of dimensions that mean something semantically, but ultimately they want to apply them to a library function that sort of, they want the library function to ignore those dimensions because it's supposed to be sort of a parallel map over those dimensions. But still they want to preserve them because they have some inherent structure without necessarily flattening them into a single dimension. In DEX, kind of for batching, you can just sort of use a top-level loop, or like in another language you could use a top-level map. And also some rank polymorphisms can be recovered using type classes. Because our array type actually is inductive, if you have an ND array, something like an addition of ND arrays can be basically derived using a type class system, right? So if you define an add instance for a base type such as int and an add instance that inductively extends it from the base type to an array, we can add matrices, and basically the compiler will synthesize sort of the 2D loop nest for something like this addition. But I'm not saying this recovers all of rank polymorphism, definitely not. So again, let's look a bit more into the type system. I will not be getting very formal here. I mostly want to give you a few more examples to sort of give you a feel of how this ends up working out in the end. Sort of the first example, and actually an interesting one from the point of view of differentiating from something like the single assignment-C expressions, is a function such as broadcast. Also, there is basically a sea of different parents here. So let me just quickly explain what happens here. So the curly braces mean that A is an implicit argument. We kind of leave out the type annotation, but it's used in a type annotation of V. So generally, we will infer that its type should be the type of types. V is basically the value we'll be broadcasting. Then we explicitly take the type, the index type for an array. And in square brackets, we specify that it has to satisfy the constraint IX. So there has to be an instance of the type plus IX for this type. And after the column, there's the result type annotation. So it'll be an array of using indices of type n of values of A. And what you can see, and the function is actually defined by this very simple expression. You can see actually left out the type annotation here again. I think that the interesting thing is that the sort of loop-bound inference is actually not syntax-driven. There doesn't need to be any indexing expression inside the loop. The sort of the return type annotation here is sufficient for DEX to infer that the only way for this program to possibly be well-typed is if I ranges over n. Because if it ranged over anything else, then it actually wouldn't construct an array with an index set of type n. In particular, if you have there's no sort of implicit subtyping happening. If you have an element of fin3, it's not implicitly an element of fin5 again. It is kind of, you would have to cast it, sort of inject it explicitly, right? Which is what kind of makes this kind of inference possible. And as an example, you can broadcast 2.0 over an index set of fin5, and you'll get a 5-size array of 2.0s. So that's, I think, a pretty neat feature. Basically, kind of hinting at how our eventual unification works, let's look at an example where we define two variables, both really express the integer 5, and they're both defined by exactly the same expression, 2 plus 3. Now, if you try to basically add arrays that use indices fin I5 and fin I5 prime, you will actually get an error from DEX complaining that, well, those two types do not unify. So we actually do a very limited normalization. When it comes to types, we will not do any arithmetic. In fact, if we cannot reduce an expression, we will not even inline it. So we will forbid something like fin 2 plus 3, right? If we were to straightforwardly inline this, even alpha equivalence would show that those expressions are the same. We kind of don't do this. We kind of opportunistically do some reduction, but very, very little, right? For an example where we do a reduction, fin5 itself is an expression, right? And fin itself is a function defined in the prelude, which is defined in terms of range, and range is defined in terms of something else. So there is some reduction happening. Mostly, it's really just inlining and beta reduction. But for example, math is never performed. And our substitution is also limited to fully evaluated things. The way it works syntactically is that our core language actually has sort of two syntactic categories. There are expressions like binary operations or for loops. And then there are atoms or values, which are kind of fully evaluated expressions, right? So something like a variable, without actually substituting it a priori, there's no more reduction rules that apply to it, right? A pair of two fully reduced things is also fully reduced in itself. Similarly, a lambda actually is sort of a lambda, sort of a function constant, is also a fully evaluated value. And what's important is that anytime there is sort of a place in the intermediate representation in the core language where we have a type annotation, we also expect the type annotation to be fully reduced. So in particular, if in here fin was actually defined in terms of some complex arithmetic expression that we cannot reduce sort of statically using this beta reduction and effectively substitution and inlining, then actually DEX will just reject this program. It will tell you that it's too complicated for it to be type checked, which is kind of a middle ground between the fully dependently typed languages and languages that have no dependent typing. But in fact, it's a middle ground that is fairly easy to explain to people, right? Like they don't run into issues like you have a type of size n plus m and n plus n, and those two are sort of, people consider those to be equivalent, but computers don't, and people get surprised when computers don't understand this. But in here, like you can tell people that there's a very sort of simple, almost syntactic criterion really on the way that they use their types. And people usually will not replicate the expressions like this and will not sort of corner them themselves into arrows like this one. So actually, this sort of typing discipline has been working out pretty well for us so far. As sort of the last feature to mention here, we do have obviously some types, nothing very fancy there. Something like the baby type from Haskell is definable index. What's perhaps more interesting is that we have product types and most importantly, dependent product types. So one of the things that you will find defined in the prelude is the type called the list of a's. And the constructor actually takes an integer, which denotes the length, and then the elements are stored in an array of that given length. Exactly. So it kind of erases or like existentially quantifies over the length of this array. And this makes it possible to implement a function such as filter, right? This is slightly different in the way you use it is slightly different than, for example, in FUTPark, where those existentials were kind of inserted automatically and unpacked for you automatically. In Dex, there isn't actually this constructor that you have to use. And when you unpack, you also can use this constructor. But you don't have to bind this to a name. If it's only used in a type, then we can kind of manage it internally if you don't need it. And so you can filter, get the valid data, and then, for example, sum it, and that program will just compile. So there is a little bit more explicitness compared to the other approach, but it also works out fine. And what's also interesting, like those lists can be nested in arrays themselves. I will be talking about that a little just in a moment as well. All right. So that's kind of the crash course in the syntax of Dex, I think, or in the very basics of syntax in the type system of Dex. The big question is, what do you get once you actually implement a language like this? And actually, this is the part that I think I'm the most excited about. So basically, I think that most libraries that program with arrays or ND arrays, they always or almost always require you to use integers as indices for arrays. And to us, that is actually kind of a big step back in terms of expressiveness. For once, static reasoning about integers is difficult. Again, for people, like explaining to the computer that n plus m is the same as n plus n is kind of awkward. This is just hardwired into our brains from like preschool effectively. And when a computer complains, like even saying, giving a proof like that is very confusing. But perhaps more importantly, integers actually erase a lot of structure from the program that is often useful to have. And sort of two good references I would find for something like that are, well, one is sort of a slogan that I find on Alexis King's blog, which is called parse and validate, which I actually really like. It's kind of a nice principle to keep as you're doing functional programming. Basically, instead of having an if that some condition holds, let's say, if my variable n is lower than 20, then I will do something else, let's say our error, instead of doing something like that, which then in the success branch kind of adds like you kind of have to implicitly keep track of the proof that the n is lower than 20. What would be better is to have a parsing function, which takes an arbitrary integer and returns a maybe fin20, right? So it's sort of, if this parsing succeeds, you kind of get a value with a type, or something like, is this list non-empty? You kind of which casts a regular list to a non-empty list type. This kind of gives you already like enough information for you to use in that branch and to be able to unambiguously see that the program will not fail. It kind of eliminates a step of sort of non-local reasoning between the condition of the if and the actual eventual usage of the value. Similarly, I really like this tweet. So every time you see numbers, you can think that a natural number is basically a list of ones, right? And you should always ask yourself what the one has actually forgotten. Basically, like, we often use numbers when you kind of don't want to talk about some entities, but sometimes it's actually useful to remember like, what are the entities that the numbers are a proxy for. All right, so basically, this is roughly what the rich index sets, why sort of we use those arbitrary index set types that are only constrained by this type class, right? So in particular, this is the definition of the IX type class. You can find it again in the prelude. So to be a valid index set for an array, you have to be able to, well, the compiler has to be able to query the size of that index set, and you have to specify an isomorphism between the elements of your particular type and a prefix of natural numbers between 0 and size -1. In particular, the cast to integers is always total, but the cast from integers is partial. But of course, you can wrap it in a and by default, it's implemented in an unsafe way. If you implement it incorrectly, you will get seg faults, but usually that hopefully should not happen in most cases. And there are also safe variants that most users should actually use when they try to cast integers to index set. This is more for performance reasons for the compiler. Now, what's interesting is that, again, Dex will not allow you to Dex will fail to normalize something like fin of n plus m as a type expression, right? Because the n plus m as two variables, it will not be able to actually normalize this to a fully evaluated thing yet. Like the binary operation plus is an expression, not an atom or a value. But basic sort of shape arithmetic is available to you basically using standard type constructors, right? If you want to have an array which is a product of the sizes of two other arrays, well, you can just use an index set, which is the product type of those two arrays, right? Similarly, if you want to have an array with the size which is the sum of two other index sets, you can use a sum type. And for exponentials, you can even use arrays themselves as indices for other arrays, which will essentially give you exponentially sized arrays. And to give you a few basic examples where that is useful, the most basic one that I would consider is, again, reshapes. Like sometimes you will have those library functions that have some conventions on how they interpret different dimensions of the data, and you will need to do some restructuring of your ND array. Like, I don't know, you might want to flatten the two middle, like if X is 4-dimensional, you might want to flatten the 2 dimensions. So you have to specify like some partial shape specification, and the reshape function will kind of do the manipulation of the data. In Dex, a transformation like that can be expressed just as a one-liner. So again, we just index X straightforwardly and just have a for loop. The interesting part here is that this thing is basically a binder. It's a binder that we immediately destructure basically using a tuple pattern, right, a pair pattern. And so this thing really will be a binder for an n by n and m sort of index sets that we immediately destructure to two sort of values j and k that are actually exactly sort of the types that X will expect, right? So there's no possibility of having out-of-bound indices here. It's all sort of well-typed and completely type-safe. Similarly, concatenation. Oh yeah, and actually what is interesting here is that sort of the resulting array, it actually remembers, right? If you flatten two array dimensions and you have integer shapes, the sort of shape of the output array from the reshape will kind of have forgotten the two sizes of the two dimensions that got flattened into one, right? You kind of have to keep track of this yourself in the surrounding code. In here, it's actually a perfectly invertible operation, right? The type of the array will indicate exactly what were the types of the indices of the two dimensions that you have flattened. And you can actually sort of construct another for expression that just is an exact inverse of that reshape. Concatenation, kind of similarly, once you concatenate to arrays, it's kind of lossy if you only keep track of integer shapes. But in Dex, well, you can just use a sum type, right? This is an n or m, or like an either m typed binder. And again, we can actually even skip the type annotation, right? Dex will infer that because you kind of pattern match and the constructors are left and right, then it has to be an either type binder. And because you use sort of the elements from the different cases to index into those array X and Y, it will kind of infer the n and m from both sides. And also what's nice here is that usually when you write a concatenation function, there's already a bit of integer math that has to happen on the indices, right? Usually you will sort of iterate between 0 and the sum of the length of the arrays. And once you get to the second array, you will have to offset the actual sort of iteration, sort of the loop variable by the size of the first array. In here, all of this math sort of on indices is done exactly sort of inside the compiler, and is basically hidden by sort of those constructors. And in any one of those cases, you already get sort of a valid index for the arrays that are interested in concatenating. Another neat thing, I think, are named axes. So one sort of common pain that I had when working with different image processing libraries is, like, what is the order of dimensions in an image? Does height come before width, or does width come before height? If you get used to one, then you switch to a different library. You will just get it wrong all the time if it uses a different convention. Again, one of the neat features in Dex is that we do support sort of row polymorphic records. And what's nice about row polymorphic record theory is that the order of fields doesn't actually matter. So you can use sort of records of index sets as index types themselves. And in that case, you can actually define your image. And it doesn't matter whether you index with an expression like this or with an expression like that. They're actually equivalent. And both will select the same element. There's no sort of confusion. Anyone can use any convention they like, and it will just work out. And finally, another nice thing is actually boundary conditions. So often if you do something like dynamic programming, you will, I don't know, have an array of size 1 plus something, and it will kind of have to explicitly, again, remember to handle the 0 case versus a non-zero case. Index, you can, again, use a sum type index set where, the base case is like a unit index, and then you have some index set n. Again, with the benefit that if you'd ever try to have a loop over an index set like this and try to use it to index an n-size array, the compiler will complain. It will tell you, well, you haven't actually, this is a unit or n index, not an n index. You are required to sort of unpack it and either handle the base case, which is the left of unit, or you get the right of index, and then you can sort of treat the usual case in your dynamic programming algorithm. And what's interesting, I think, in this is that it's actually, this is a hypothesis because we actually do not sort of take advantage of that at the moment. But I would imagine that it's not only useful for users, but it's also useful for users to express their intent to the compiler, right? If you take something like concatenation of 3 arrays, there's quite a bit of integer math, right? You might want to compile this into, let's say, 3 flat loops that fill the buffer, and you first copy one array, then you copy another array, then you copy the third array. And if you have to do basically some sort of range or range-based, interval-based sort of reasoning to actually infer that in the first part of the loop this condition will be true, then this branch will be taken, and then always this branch will be taken. If we actually, let's say, assume something nice about the property about the either index set, that all of the left indices come before all of the right indices, which we can do if we provide it in the prelude, for example, then a loop like this trivially can be split, right? Like we will know that first the index I will always satisfy the left, and once we run out of the lefts, it will only always satisfy right? And similarly, the sort of nested either, this will be true again. So something like actually splitting the single sort of loop that concatenates those 3 arrays inside the compiler, again, you might want to work over a slightly richer language than the surface language that we have here, and I don't know, talk about mutable buffers perhaps. But it will be much more natural than to do integer-based reasoning, I would claim. And another sort of neat feature of this whole thing is what I like to refer to as indexing lemmas. Basically, as you use integers, as people often use integers in indexing, as people use integers as array indices, you will often find sort of fairly non-trivial indexing expressions scattered all over their code. Like, for example, if you want to reverse an array, you will often use a sort of expression that looks like length of the sequence minus 1 minus I, right? It's not a super complex expression, but also like, why does this should the minus 1 be here? Is that an off by 1 error? Like, it's not immediately clear. And if you have the reasoning about this expression being a correct index for the array also requires you to think about like the values that the I variable will eventually be taking. It's like there is some non-local reasoning happening here, and it's not an immediately trivial proof, right? On the other hand, if you use like structured index sets, there's, for example, a lemma you can write index, which I call reflect, which basically means if you have an index of an index set somewhere, then there's always like a reflection of this index with respect to the middle point of the index set, right? If the index set is empty, then this is still satisfied because you will not be able to produce even an index, a value of that index set. But if it's not empty, then there's always a valid corresponding index. And it's defined exactly as that same sort of arithmetic expression and sort of an unsafe cast. But what's nice about it is that sort of you prove the correctness of this index to index conversion entirely sort of separately from any program context that it will later be used in. And it's kind of a reusable thing that it will be able to apply multiple times, right? And so this code actually simplifies. Obviously, this direct comparison is not like a huge deal, but if you were to use this many times, it might actually help you prove that your program is correct. And similarly with dynamic programming, another benefit of using this unit or n sort of index set is that there's again a valid indexing lemma which says, well, if I have an index of type n, then there's always a previous sort of you can always get an index to a previous element in a unit or an array, right? If you have a unit, basically, if this is the first element of n, then you get the unit. And if this is not the first element of n, then you get, well, basically the previous element in the index set of n, right? Which actually has a super trivial body with, the return type, again, being to avoid duplication of the return type here, you can basically leave a type 12 for the compiler to fill in. And again, like instead of having an expression like that, which kind of is only valid if this expression succeeds, which again is this sort of This is kind of the validate approach. This is more of a parse approach. You get kind of a structured index. It's either the base case, in which case you do something, or it's not the base case, in which case you can actually get the right index. Oh, sorry, this should be I prime. Oh no, sorry. Okay, this is correct. In which case you can actually use the sort of previous lemma to actually be able to do something like sum the neighboring numbers in another array. Cool. And also index sets are user definable, right? So in particular, we can have like a data declaration for red, green, blue. We can define an NIX instance for it. You can have one for the HSV color space. You can define an image to be essentially a type alias for, again, an array which uses the record type of height and width, and then the color space, and then like quantized values for every pixel. You can load like a known size JPEG with this type. You can convert it to HSV. And if you want to extract the hues, this is like the indexing expression you would use. Again, you can swap out the height and width pretty much as you see fit, right? And for example, if you forgot if you use like 0, 1, 2 as indices for the different sort of channels in your color space, if you forgot the casts between like RGB and HSV, and you used up, I don't know, the first, let's say, element here, you would basically be looking at the red channel, which is obviously not what you want to do in here, because all of both of those are actually isomorphic to fin3. You do have the extra structure in the labels, and so kind of those arrays can also function kind of like statically checked name tuples in some languages.
Adam, there's a question from Martin.
Yep.
Hi, sorry, I think it's a critical point of the lecture, so I just wanted to make sure. If you go one slide back in your previous example, so if the array is empty, then this transformation to unit and n is not valid, right? So if I understand correctly, the compiler wouldn't guarantee that there's no indexing error if it happens to be that this particular array is empty. Is this correct?
Right. I mean, this particular piece of code, like this for loop, will be over unit or n, and I assume that I have a variable like this x here would be fin1 plus s or 1 plus n, and in here it's x with an index of unit or n. If you have if you take in an arbitrary array, which a priori you don't know if it's empty, there might be another lemma, again, in the parsing spirit, which takes an array with an arbitrary index set and gives you back like an array with a unit or something index set, like maybe that. And in the success case, you know that your array was not empty.
Yeah, actually you'd pile something else on top of that, but this particular thing doesn't prevent you from. Okay, thank you.
Yeah, I mean, in this example, it still works out, right? But if you were to write a function which is polymorphic over any array, then yeah, you will need to add an extra check that the array is not empty. But again, you can try to phrase it in this sort of parsing scheme, not, instead of saying if size of my array is not 0, then I will just assume it. Again, you can try to cast it to an array, which clearly is non-zero because it's 1 plus something.
Thank you.
Yeah, but good question, thanks. And sort of the final benefit, I think, from, again, trying to think about arrays and functions in the same way is, well, we have implemented this whole language with dependent functions. Why don't we just try doing dependent arrays? What does this mean once you have dependencies between the dimensions of your array? It's kind of a natural question to ask once you go there. And in fact, I mean, we weren't the only ones. That later we've learned that sort of independently others have developed sort of very recently again some theory for that as well. But I will sort of show you how this looks in the context of DEX. So sort of this is a little made-up taxonomy of array types that we formulated some time ago, sort of ranging from the most homogeneous to the most heterogeneous arrays you can possibly get here. So at the sort of homogeneous end, you have arrays with entirely static bounds, like here at 10 by 20 matrix. Then once you have a value-dependent type system, you can go sort of to the dynamic case, so n by m matrices for some statically unknown n and m. Then the interesting part are arrays that are rugged. They're no longer rectangular like the first two, but they have some structure. And a good example here are actually triangular arrays. And so this is a type which is a valid type for a DEX array. So the first dimension is of size 10 for simplicity. But what's important, this will be a dependent table arrow. So we already in the type name sort of the index that will be used to index into that dimension later. And that we indicate that the type of the second dimension is .. .i, which roughly means the restriction of the index set to which I belongs to elements that are up to I inclusive, right? And so if you use larger values of I to index into, to select the row of this matrix, you will get progressively longer rows, right? And so exactly what this corresponds to is a triangular matrix. And in fact, DEX can do like some reasoning in arithmetic to, again, flatten this whole type into like a flat vector and derive like indexing expressions.
What you can't do there is have just finite.
Right. You could have in this case you could have finite, but this dot 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 also works like if I is of R, like this could be an n for some index at n, right? And that would still be a valid type. But yes, in this example, I think finite would also work.
Okay.
Then sort of going to more unstructured raggedness. So really sort of arrays where the rows can have any length. Sort of there is a sort of made up distinction between ragged and jagged arrays, where ragged are sort of slightly more benign, I would say. Again, we kind of bind the index used to index into the first dimension, and then we say the size of the second dimension is given by looking up the ith element of some length array. And if you think about it a little bit, that is actually exactly the CSR representation of sparse matrices, right? With the sort of lengths giving the lengths of the rows. But yeah. And then jagged, essentially, we use the list type. Again, as I've mentioned, lists can be put into array themselves. Those dependent products can be stashed into arrays themselves. So in here, we have, again, a size 10 sort of, we have a bundle of 10 sort of arbitrary length arrays, which in expressiveness should be roughly similar to the ragged case. What is interesting is that this ragged case exposes a bit more information to us in the type system. So for example, if we see two values with this type, we can actually zip them together, right? We can iterate over an index set that looks like this. If we have two values of type like that, once we unpack sort of the rows, like let's say the ith row of every one of them, there's no guarantee that actually those rows are of exactly the same length. One note, though, is that this length that I actually would be pushing the limits of our type system, and actually we do not support an expression that looks like that right now. We are kind of planning to add some extensions to make our type system more powerful, but except for this one, all of those types are actually valid DEX types that you can even play around with today. All right, so that sort of completes the part about the front-end language, and I think what are some of the sort of exciting benefits you get from having a front-end language that looks roughly like that. Now, sort of, I wanted to basically discuss some of the implementation challenges, especially again around AD, that you get once you try to implement a surface language like that. Most of that was in our paper, but I don't know, it might be helpful to see just it explained live. Basically, if you look at the sort of compilation pipeline that DEX uses, I mentioned a part of it. We start with like untyped surface syntax. We use type inference to sort of elaborate it into this value-dependent core language. Then we have a step that normalizes those sort of very functional expressions to effectively first-order programs where functions are no longer values. In particular, this is where sort of heavy inlining and monomorphization happens. This is a fairly standard step, I think, in languages like that. In particular, there is actually even a paper based on about how FATHARC does this. And this is also the step where automatic differentiation happens, and we'll discuss this loop in a second. After that, what happens is basically a bunch of optimization, parallelization decisions, and code generation. Although there are definitely people who are better in those things right now than we are. So for now, we'll actually focus on this level because this is, I think, where some of the interesting contributions that we have had are. So let's zoom into how AD actually works. So basically, AD comes usually in two flavors. There's forward mode and there's reverse mode, with forward mode being kind of the simpler one and reverse mode, sadly, being the more useful one in practice. So forward mode AD, we implement using a function that we generally call linearize. So it's a higher order function. It takes a function argument, and then it returns another function, which looks very similar, but it's actually augmented by an extra return, right? So if you take a function from A to B, and here I will also, for simplicity, assume that A and B are some vector spaces, what you will get back is, again, a function from A that also returns a B, which will be exactly sort of semantically equivalent to this B. But it also returns another function that where I use this sort of lollipop arrow to denote that it's actually a linear function, right? with the implication being that this function is actually a derivative of this function at the point at which you applied here, right? And then the sort of the a's here are sort of the directions. And if you try to evaluate this function on a set of directions, you will get a bunch of directional derivatives, right? Which sort of live in the space of B. So that is roughly forward mode AD, or at least a flavor of forward mode AD, because you can actually define other ones. But that's not for today. What is sad is that we often want actually a representation of this derivative mapping, right? Here it is represented as a function. We often want it as a matrix, right? In particular, the interesting case is for gradient-based optimization is when B is a scalar and A is a very high-dimensional space. Think like a billion parameters in a neural network. You will want the full Jacobian, which in this case is like a billion by one matrix. So one way to do it is, well, we have this function. And so if you want the Jacobian in some basis, what we can do is we can basically try to evaluate this function over every single basis vector. But obviously, if your input vector space is like billion dimensional, this is very expensive, because the evaluation of this function is basically at most a constant factor, as expensive as the evaluation of this function. But there's sort of, to the rescue comes another nice property of linear functions, which is that actually every linear transform has a transpose. And so sort of to complement this and to make this much more efficient, we also implement another higher order function that only works on linear functions. And in fact, we have a slightly stronger requirement that they're not only mathematically linear, but also what we call structurally linear. There's basically some invariance on actual bodies of those functions. But if you give, in particular, linearize always produces functions that satisfy this invariance, and so they can always be transposed. And transpose is pretty magical because it basically inverts the data flow, right? If you give me an A to B function that is linear, I will give you a linear B to A function, right? And in particular, reverse mode AD is implemented by linearizing one function and then transposing this derivative mapping. And then, if this was a scalar and this is a billion dimensional vector space, then you can just instantiate this at the basis of the, I don't know, reals, which is, let's say, a scalar 1. And what you get back is the Jacobian matrix that represents this this particular linear transform. This sort of way of decomposing AD, we actually haven't. We use it pretty heavily in all of the projects that we work on, most notably in JAX and in DEX. We only have, sadly, a very short note that describes it, although we are actually working on a longer form presentation. And it's, at this point, I probably have said this multiple times in talks, but at this point, it is very close to actually being finished. And so hopefully within the next month or two, we should be able to actually put it up. And so, but for now, you will have to sort of believe my hand waving that this is possible and that this works out, and you can implement AD that way. Cool, but so the big question is, how do you implement linearization? So let's walk through a few examples. Basically, if you have, for example, linearize a function which just multiplies two numbers, well, the primal computation stays the same, and the derivative is just the derivative rule for multiplication. Nothing very special happening here. If you have a function composition, well, what this will elaborate to is basically a linearization. We will linearize the first function at the input point, bind the temporary result and sort of the derivative of that function at this point. Then we will do the same thing to the second function, but at the temporary point, get the derivative, and then just compose the derivative and return the result, right? This is effectively an encoding of the chain rule, right? Which says that if you have a composition of differentiable functions, then their derivative is the composition of derivatives at sort of the points, the primal points sort of slightly adjusted according to how the composition flows. Now, the big question is, how do you linearize for loops, right? This is kind of the new language construct that we have here, and we have to deal with that somehow. So if we have a for loop, which is somehow defined by a body function f that takes x and I, how do we do that? And there are basically two methods, at least two methods that you can use. One simple one, which you could do is, well, you could basically say that the primal expression stays the same. Oh, I missed the parents here. F was meant to take a pair. But what you could also do is, so primal expression stays the same. And then in the derivative, only then do you actually end up linearizing the function body. Then you sort of throw out the primal result, and you use sort of the derivative of the body instance at sort of the perturbation for that body, right? In particular, the for loop like that, it's basically a bunch of independent parallel computations. So if you take the derivative of something like that, it's again a bunch of independent derivative computations. Now, this would work out. This is well typed and actually computes the right thing. The only downside is that this linearization here, it will have to recompute exactly what this expression here has already computed once. And so it's actually throwing away a lot of work. And that gives you an AD system, which is not exactly efficient in the way we normally like to consider AD systems to be efficient. But there is actually a workaround, but there is a requirement that this workaround, to use this workaround, you will have to allow arrays of functions, which is generally something that languages in right now rarely allow you to do. So there are some caveats there. But so the idea is that if you could have arrays of functions, what you could do is you could, again, have the for expression. You could just linearize every instance of the body. What this gives you is sort of an array of pairs where there are the original results and the derivatives of every instance of the body. We can unzip that array. We can return sort of the array of results. And the derivative computation essentially has a for over the linearizations of the instances of the body applied to sort of the linear version of the ith instance of the body is applied to the ith perturbation, right? And that sort of gives you the right thing, again, with the caveat that you have to support arrays of functions. In particular, for example, FADHARC, I think, has this restriction that this is not possible. But it turns out that actually it's not that difficult to add. And in fact, this is what DEX does. So imagine that we have a function that's called 2 first order, where if we have sort of a context here represented as the nest of declarations, they can be arbitrary declarations in the core language. So in particular, you can bind function types. What we will want to transform it to is, What we will want to transform it to is a context which only has sort of first order binders. There will be no functions bound in that context. And then a substitution that should let you reconstruct essentially the original value. So this will be a substitution that maps all of the names bound in here to atoms, including lambdas, that can only refer to this first order context here. And so, this is not entirely trivial, but it's also not that complicated if you think about it. If you have a context where you bind a result of a for loop to X with some for loop body, what you do is you normalize the body of the for loop to first order. And then when you have sort of the value that this body returns, what you do is you sort of apply the substitution that reconstructs to this atom. Now this will only have free variables in this particular context or from outside of the for loop. And you only have to sort of save the things that will sort of disappear from the scope as the for loop exits. And those are those A1 to AKs. And sort of this is the for loop that you will eventually emit. And then to produce the substitutes, OK, so you normalize the block. You find those first order variables defined in the for loop, which is what this intersection does, sufficient for this reconstruction. In particular, if this atom was a function itself, right? So if this was defining a for loop of a function, the nice thing now is that either all of the function valued function typed atoms in there can either be functions that are defined outside of the for loop, and so the intersection will just eliminate those because they will not go out of scope as we exit the for loop, or they are lambda expressions that mention some free variable, some first order free variables that are defined in this body, right? But if they are lambda expressions that sort of mention those variables, then well, we can reconstruct them pretty easily, right? What we do is we take this, we say that to reconstruct X, we use this sort of lambda, we use this lambda for the table type. So this is normally sort of, let's say, frowned upon in the surface language, but it's something that is convenient to be used internally. It basically constructs something of the table type, except it's not sort of eagerly evaluated, which we use for those substitutions. We basically we again apply the recon subs to atom, which will make it refer only to FO1 to FOM or things from outside of the for loop. And then we unpack the ith element of this sort of first order array of first order values and use that to satisfy the free variables A1 to AN. So this was a bit technical. I don't need you to follow exactly this, but sort of this is a sketch of how you can do this. And in fact, if you want to do efficient differentiation of case expressions, you will also need to do something like that. And this is also why we have this loop here, because automatic differentiation, like it's convenient to consume, like differentiate a language which is first order and does not have any functions in it. But it is also convenient to produce, by the means of automatic differentiation, a language which might use functions as first class values again. But instead of sort of special casing, like building up the tape effectively, this is what those closures are in automatic differentiation. What we do is we basically loop where if we see a call to differentiation of some function, we will normalize it. We will apply AD. The result will come back unnormalized, but we can normalize it again and basically do it inductively if AD is nested. So this is sort of why this loop is in there. All right, so we're kind of running out of time. So for the second issue, I'll have to be a bit quicker. Basically, the idea is that now let's consider implementing transposition. Basically, those are roughly how transposition works for addition and scaling, but we can skip those for now. The interesting parts are, for example, in duplication, a function which takes something and actually just returns twice the same thing. You can think about representation of that linear function as like a matrix that has two ones, sort of, over the right field. And so if you try to transpose a matrix like that, what you'll get is a linear transform that actually takes two inputs and sums them together. And so the interesting part is that sort of the fan out, which is kind of implicit in the one computation, will turn into addition in the transpose computation. So in particular, if you have a broadcast, if you broadcast a value to an array, in the transpose, you will have to sum all of the perturbations from that array to get the result. Now, the big sort of difficulty, really, transposition mostly works out fine. The big difficulty sort of appears in indexing, because the question is, what will be the transpose of an index, right? If you think about it, indexing, like the representation of an indexing is like a matrix with all zeros and only a single one in the place in the index from which that you project, right? And so intuitively, you would like to kind of only increment sort of the ith element in a perturbation that looks like that. That is normally how it's implemented, for example, in imperative languages, which makes it sort of seem very easy. But we're in a functional language. We don't want to introduce arbitrary mutations. So how do we do that and still be efficient, right? Basically, sort of there's an unstated cost model that if you index out, let's say, a row from a matrix and then a vector from a matrix, then it's a constant cost operation. But if you try to update an element of a row and then put that row into a matrix, that might incur some sort of more expensive operations in a functional language, and you kind of don't want to pay for that if you have an efficient AD system. So we might need to alias writes just like we alias reads. So there are multiple approaches to this. Again, imperative ID just loads, updates, stores. We don't want this. That's unconstrained heap mutation. You could do dense updates where you instantiate those matrices that are full of zeros except for like a single one. But sadly, that has lots of wasted work and gives you an AD system with like wrong asymptotics when it comes to efficiency. You can do sparse updates, but this is really bad constant factors and it's kind of annoying on GPUs. You can do, if you have a linear type system, you can actually do it sort of with the linear updates. The big problem is that this sequentializes code. If you have a parallel loop, the ownership, and you then try to sort of turn it into a loop like that, you have to express the passing of ownership between the different loop iterations, which sort of necessarily sequentializes the different loop iterations, which is not ideal. So actually, what we ended up settling on is an associative accumulation effect, which roughly looks like this. There's an effect handler, and obviously we enriched our type system with sort of row polymorphic effect types. So there's an effect handler that gives you a reference to an accumulator. And in the body of that handler, you can only increment the accumulator. You can never actually read the value of that accumulator. But once this handler exits, it returns you the value of the expression that it holds here and the total sort of final value of the accumulator after this whole expression terminates, right? So what's interesting is that in particular, this can still be executed in parallel. If you decide to parallelize that for loop, you can literally just replicate the accumulator even between the different threads and then reduce it at the end. So that does not sort of inhibit parallelism in our case. And for AD purposes, you actually don't need to read this accumulator before it has been fully formed. So that's like a very good sort of workaround that we found. Similarly, once we've had this, we also added the state effect, which lets us define something like a scan without recursion and without it being sort of a built-in combinator into the language. It's just defined in terms of the state effect and the for loop. Obviously, this is not parallelizable anymore. And once we've defined the basic accumulation effect, it was also fairly straightforward to extend it to arbitrary monoidal reductions, which means that reduce is also not a combinator in the language. It is defined entirely in terms of a for loop that has an accumulation effect and still can run in parallel if only you parameterize it by some valid monoid, so an associative function with a neutral element, right? The interesting part is actually differentiating something like that was not trivial. We do have essentially a paper from FHPMC from last year that talks about this, actually, if you're interested. So just to sort of close this whole section, I think the interesting part is that efficient AD is a very, in my opinion, it's actually a very good sort of language design benchmark. Like if your language can support efficient AD in the sense that, you know, the cost of evaluating, there's a constant that is independent from the program that you look at, such that if you apply either forward mode or reverse mode AD to your program, then actually the cost of evaluating that differentiated program will be at most that constant larger than the original program, right? If you want your language to satisfy this, it has to actually be sort of closed under two properties. It has to be closed under partial evaluation, which is kind of what linearization does. And this is kind of the part where we had to deal with those functions. And it also has to be closed under data flow duality, right? So in particular, if you have sort of implicit fan out, if you can like broadcast a value, then you should also be able to like reduce a value. And so what's interesting, actually, going back to that paper about differentiation of second order languages, the sort of parallel associative scan primitive actually does not let you implement AD efficiently because it is not closed under partial evaluation. And so sort of the standard definition of the SOAC languages actually does not satisfy this. So I'm sure there's like a smart sort of category theory basis to say what I just said here. But I, you know, sort of stated very much in like programming language based terms, this is how I would see it. And actually implementing AD in this way, I think does sort of regularize your language in a nice way, just like sort of AD led us to actually implement all of those effects, which did end up being, I would say, a very sort of welcome addition to the language that our users have been actually enjoying. All right, that's everything I have. Sort of as the last part, perhaps I just thought I'll mention some of the potential directions we're heading in now. So we kind of want to push on the algebraic effects front even more. So we actually have sort of a PEPM short paper submitted to PEPM about sort of user extensible parallel-friendly algebraic effect systems. We did some work, or mostly Dougal actually did some work on ensuring that our compiler implementation is scope correct, like we're not forgetting to apply substitutions. This is just work entirely in Haskell, but actually it's been a huge deal, and it has like caught so many bugs since we have implemented it, which we also are sort of in the process of writing up. Another one is, well, the defunctionalization or normalization to first order, it actually requires a lot of inlining that just blows up the program size. It makes for very bad compile time, so we're kind of working on harnessing that a little bit, on controlling this. Another thing, which actually I would find very interesting, is Julia actually shines very much at multiple dispatch. And you can achieve multiple dispatch with multi-parameter type classes. But what's interesting is that Julia also heavily embraces overlap, which is, for example, disallowed by Haskell. And they're using it to a great degree and with very high success. So I would be kind of interested in how we can work around a type class system to still be able to statically resolve most calls, but still allow some sort of controlled overlap because people are actually doing very reasonable things with it. Another one is nested data parallelism. I really enjoyed Connell Elliott's earlier presentation. I think in the last sort of edition of this seminar, I think that sort of we have somewhat similar ideas with those structured index sets and sort of viewing arrays as tries. The sort of big difference is that DEX actually does not support recursion right now. And once we have recursion, we probably want nested data parallelism. So trying to figure out kind of how to express things like that in DEX. I think we're kind of on a good track, but we're still kind of not entirely there. And I really want to take us all the way there. And finally, just really make it fast. And there's also a bunch of other threads of work, but I am really over time now, and I should really finish. So that is everything I have for today, and I'm happy to. Thanks for listening, and I'm happy to answer any questions.